Hey everyone, welcome back. Today we're diving into a groundbreaking study that's transforming how scientists tackle one of the most insidious environmental challenges: surface ozone pollution. This invisible yet dangerous pollutant forms when emissions from vehicles, industry, and natural sources react in the atmosphere. But here's the kicker: predicting its behavior is a complex puzzle. Traditional models struggle with the fine details, leaving gaps in our understanding. That's where cutting-edge AI is stepping in. And today we're unpacking how uncertainty quantification is helping researchers make smarter, more reliable predictions. Let's start with the problem. Air pollution is a global crisis. In 2023, 94% of the world's population breathed unsafe air, with surface ozone, a key component of smog, posing a major health risk. Unlike visible pollutants, ozone is invisible, yet it irritates lungs, worsens respiratory conditions, and even contributes to climate change. The challenge: ozone levels depend on a tangled web of factors: temperature, wind patterns, sunlight, and land use. Traditional climate models, while powerful, often lack the granularity to capture these dynamics accurately. Enter deep learning. Researchers are now using AI to create emulators, simplified models that mimic the behavior of complex systems. But here's the critical twist: even the best AI needs to tell us how confident it is in its predictions. That's where uncertainty quantification, UQ, comes in. Think of it like a weather forecast that doesn't just say, "It'll rain tomorrow," but also adds, "There's a 70% chance of downpours, so bring an umbrella." The study focuses on a model called MOMO-Chem, which combines satellite data, ground station measurements, and environmental variables to estimate ozone levels. But even this advanced system has biases, systematic errors that skew predictions. To address this, researchers trained two AI methods: Monte-Carlo Dropout and Conformalized Quantile Regression. Let's break down how they work. Imagine the AI is given a dataset: temperature readings, wind speed, satellite imagery, and land use information from Google Earth Engine. It uses this to predict where ozone levels might be off. Then it calculates the uncertainty of those predictions. For example, if the model is unsure about a region, it flags it as a high uncertainty zone. This helps scientists prioritize where to collect more data or refine their models. Here's where the real insight lies. The team found that adding land use data, like whether an area is urban, forested, or agricultural, slightly improved accuracy. But the bigger revelation was about uncertainty. Both methods agreed on some regions, but disagreed on others. Take the east coast of North America and Southeast Europe. Both models flagged these as high uncertainty zones. That's a red flag. These are places where the model's predictions are shaky, and where we need more data or better understanding. Why does this matter? If we can pinpoint where ozone predictions are unreliable, we can target interventions more effectively. For instance, high uncertainty zones might need more ground sensors or better satellite coverage. The study also revealed dynamic shifts in uncertainty over time. On the East Coast, for example, uncertainty was broad in early June but narrowed by month's end. Meanwhile, the CQR model identified shifting hotspots in the Northeast, like a living map of uncertainty. But here's the catch: even the best models have blind spots. In the Southwest US, where data was steadier, the CQR model achieved an average error of just 7.18 units, comparable to a weather forecast that's off by a few degrees. On the East Coast, though, the same model had an average error of 14.36 units, like trying to predict the weather in a storm with a broken barometer. So what's next? The researchers plan to expand their analysis to more regions and test other uncertainty quantification methods. After all, if we can better understand when and where models are uncertain, we can make smarter decisions, whether it's planning a hike or addressing climate change. Thanks for watching. If you want to dive deeper into how AI handles uncertainty in environmental science, hit subscribe. And let me know in the comments, do you think AI should be trusted with critical predictions like air quality? Let's discuss.